how many slides do we have? We have, we have about 10 slides. Okay, okay, finish. Okay, so it's already started recording, so I'm going to continue. Now, next I'm going to talk about cation exchange, the reaction, how it happens, and I believe this one I have already explained, so I'm going to skip the equation on top. However, I'm going to stop for a while and discuss a little bit about absorption capacity. Not absorption, I believe this is wrongly spelled, it should be AD, adsorption capacity, in decreasing order. Now you can see the strongly adsorbed is aluminium. The weakest is sodium. Why this is so? Actually, there's a pattern. I'm not sure if you can see the pattern. Because those that sit nearer to the left, they usually have a large charge, 3 plus. And in fact, if there are Fe over here, it's probably going to sit somewhere before, either before H plus or after H plus. Because this charge, they have very high charge and they can attract very strongly, and that is why they can absorb. They can have a very high capacity. How they have a lot of these cations that can be absorbed, and which is why they have high capacity. Whereas those that are sitting at the right hand side, they are usually quite large, and also they have 1 plus charge, just single charge. Also, you can see less charge, they attract less strongly. And usually that is also the basis of how do we determine the absorption capacity, the likeliness of this cation being absorbed. Now, actually, there is another word that we can use over here. It's called charge density. Now, this one I still remember also because I taught this one in general chemistry before. And like I said, I think we just save it for like yourself. Like you just go back. If you don't know what is that, how do we determine why it is so? It's due to charge density. And in fact, I think after this, there are several slides that also like can show you what is that. Let's see the next few slides. Now, as a comparison, cation exchange. Now, after this, if you like have any, oh, by the way, now just a recap of what you're going to do for experiment 9. Now, experiment 9 previously is supposed to be experiment 10. However, in that experiment, you were not going to do the experiment on cation exchange capacity. What you'll be doing is you'll be shown a video. So you watch a video, how it should be done, assuming that you did it. You'll be supplied with some experimental data. So everybody will use the same experimental data to calculate CEC as well as to have some discussion on interpret what are those results. And I think this table are going to help you greatly because these are like the usual or the common CEC values from clay as well as humus. And I don't think I need to explain too much. Now, coming back to what I told you earlier, if a farmer wants to increase the fertility, they are not adding clay, they're adding organic matter because humus is an organic matter. And see how high is your CEC? Yeah, very high. And the good thing is that not only they can increase the CEC, they increase a lot of other things. Nutrient, aeration. There's only one thing that they don't increase. In fact, they decrease. And that is soil bulk density. Adding more humus increase everything except soil bulk density. Well, that's what I can remember. Probably they can also decrease other factors as well, but this is what is usually involved, yeah? So it's always a good idea to add organic matter to replace fertilizer, to have a better soil structure and to improve the soil fertility. Yeah? And it's not surprising to see like extremely high CEC value between 150 to 300 centimole per kg. And I can safely tell you, your seniors previously who have done CEC based on the soil that you collected behind Day 1 Kuliah, DK Delta, and also near Faculty of Law, those soil have between 1 until 10 centimole per kg, which is very low. Now, if you have all this kind of material like humus and also 2,1 clay added, vermiculite or montmorillonite, 2,1 micelle clay, they actually have a lot of negative charge to offer and they can increase the CEC. However, compared to humus, adding vermiculite and montmorillonite is probably not a good idea because These are not light. They are in fact quite dense. They're quite heavy. And if you add it with your clay, what will going to happen to your soil is it will have a very high soil bulk density. Is it good or bad? Well, it's probably not the best for the soil. Yeah. Because it's always a good idea to have low bulk density so that they can encourage biological material like a soil organism to live inside. You have more soil, your soil will usually take care by itself. Yeah, the nutrient will recycle. And then finally, sequence oxide, those clays that do not swell. So you can see the clays who do not swell, yeah, they're good for construction, but they're lousy for agriculture. They don't have high CEC value. Okay. So there's always something good about clays, whether it's 2-1 micelle clay or 1-1 micelle clay. Then CEC for some different kind of texture, sand, as we know, large particles, less surface area, and therefore CEC also might suffer. The one that can have high CEC usually on the clay side, clay loam or whatsoever. So why CEC is an important soil property? As I told you earlier, well, if CEC is high, they can keep nutrients. Not only they can keep nutrients, they can immobilize. They can have a role in the remediation. Where, like for example, the landfills that we build, the landfills that we build, usually will have a thick layer of clay. Now, not because the clay has abundance and whatsoever, but clay actually have its job. They have function. Clay, for your information, likes to absorb water. If they absorb water, they expand. There's only one type of clay that they use in this purpose, and it's 2-1 layer. It's not 1-1. In order to have the swelling effect, if they are swelled with water, they actually can compress, expand, and they block all the small pores that might cause the leachate to flow out. That is why your landfill usually will use monopolyolonite clay, the one that can expand. Yeah. Okay, that's what they form a impermeable layer to stop the escape, so to stop the pollutants from escape, the pollutants from landfill to leach out and harm humans. But there's another reason. These clays, as we know earlier, the expandable ones, the expandable clay, also happens to have high CEC. And because of that, whatever the heavy metals they have inside the landfill, they will be trapped by this clay. So that is why clay is so important in terms of construction of landfill. Okay, soil physical properties such as soil shrinkage, swelling, and cohesiveness. Well, that is also the parameters or the behavior that might be exerted due to the content of clay. As you know, clay they can shrink as well based on the water content. Okay, CEC is controlled by 4 factors. Soil texture, of course. If you have more clay, you'll have higher CEC. The clay type, of course, there are 2 types of clay, swellable and non-swellable. Of course, swellable ones will have higher CEC. The content of organic matter. The more organic matter, the higher the CEC. And of course, soil pH, higher pH increases more CEC. Okay, so I think we're going to go very fast because I think the major part that you need to focus just now was cation exchange. So now we're going to go to cation behavior at the exchange site and so on. Okay, the behavior. The negative charge surface of the clay micelle strongly attracts cation, cluster most densely micelle, cation most on the micelle. I think that's a repetition of what we have discussed earlier. And I think I'm going to move fast forward. I'm going to start with whatever that I have. Okay, 2 important factors control selection of cations. Yeah, this happens to be the more detailed, the more technical ones that I showed you earlier. Earlier, remember there's this one, yeah, this one. I show you the absorption capacity. The left-hand side will be more absorbed more than the right-hand side. And the scientific explanation is right here. So why aluminium can absorb more into the soil? Yeah, that is because of this one. The number of each cations and the relative bond strength of each cations. So the bond strength here involves on how strong is the electrostatic attraction that a cation can form with a negative charge surface. Well, I mean, the sequence of absorption capacity that I showed you earlier indicates that. But here we are going to learn why they behave such a way like that. Now, this sequence or this arrangement is exactly the same that you saw earlier. Now, I think I won't want to explain too much about charge density. Just watch the video and look at the description. What is charge density? Anyway, those are general chemistry. I hope you still remember what you learned in general chemistry so that you don't need to like stop for too long and learn this one. Anyway, simply put it this way lah. Simply put it this way. Any charge that have large charge, any cations that have large charge, that will have a stronger bond, and therefore they are strongly attracted to the negative charge of the plate. And the second factor is the number of each type of cation. Now in this case, is something related also to chemistry, also general chemistry. Now, in this slide, the principle, we call it, the principle that applies here under chemistry is Le Chatelier's principle. Yeah, Le Chatelier's principle. Now, that is the principle in the chemistry subject that explain exactly what happened here. Okay, now you can read as much as you can, but you also have to understand what happened, isn't it? Now, whatever they explain here, already explained, I mean, semesters before when you learn general chemistry. How Le Chatelier's principle work? How does a cation being released due to the changes of certain condition? That exactly is what Le Chatelier is talking about in regards to this slide. Now, in this case, let's look at the example, yeah? Treatment of high sodium soil with gypsum. In high sodium soil, many exchange sites are occupied by sodium. Addition of gypsum, calcium, replace sodium on the exchange site. The replaced sodium enters soil solution. Now, this is actually a treatment process, a real life treatment process to address the sodic soil problem. Now, earlier when we learned about EC, electric conductivity, we learned about uh, saline soil, remember? Now, saline soil usually associated with a soil that have a lot of sodium chloride. Exactly this one. Now, soils that have high content of salt or sodium chloride will not have strength at all. They have no strength. Meaning that the soil, if they comes in contact with flowing fluid like rainwater, you can just look at it and they just disappear, just like Thanos snap. Yeah, they just disappear because any soil that have high sodium content is just like a salt. They can dissolve straight away and then wash away, just like that. Now, what happened to the agriculture? Well, I told you earlier, isn't it? Sodium is toxic to plants. So again, nothing can grow. Not only they don't have strength, they also cannot grow. So double whammy. Cannot do agriculture, nor they cannot use for construction. Now, how do we address this problem? There could be various ways. In fact, three, I would say, three ways. Now, one of the ways is you add gypsum. Now, gypsum, the chemical formula is calcium sulfate. What are the parts that is applicable here is the calcium. So now, the soil already have high content of sodium. What does this calcium do? Now, by adding this gypsum, the concentration of calcium in the soil increase. So they increase. So what happened to the sodium? Now with the increase of calcium, they will start replacing the sodium in the soil. So actually this movement, you can say is a cation exchange. You can say is a cation exchange process. However, this process is made possible due to Le Chatelier's principle, because we suddenly increase the concentration of calcium. And because of that, this calcium can go in and replace the sodium in the soil. And because of that, the sodium becomes removed, and the sodium removes, and they are displaced. They enter the soil solution, whereas the calcium is retained in the soil. Now, the best part about having this one is that the soil, once they are replaced with calcium, they become stronger. They no longer like disappear due to the washing of rainwater. So I hope you understand what I explained earlier. If you don't, the principle is very simple. Lee Chatterley's principle. Go back and have a look. Have a look at that your chemistry textbook, and that might well explain it. Okay, the next part is anion storage. Now, anion is also one thing that people look at because why? When you look at this anion, what are they? They are nutrients. Hydrogen phosphate, extremely important for normal plant growth. So does nitrate. Well, how come nitrate is not here? Well, nitrate, I bet you, nitrate is a major one. Yeah. Nitrate is the most important anion that needs to be absorbed by plants. Why? Why it is such a big problem? Because as we learned earlier, all the colloids that you have in the soil, majority of them, they are negative charged. So when this comes in, they repel. This anion technically cannot stay too long in the soil because of the electrostatic repulsion. Now, that's not the end of the story because what? Somehow these anions still end up in the soil. But how is this possible? Well, all you need is you need a few more cations, that's all. Because cation attracts anion. And if you have cations such as those that have more than one charge, like calcium, and like your magnesium, maybe iron or maybe aluminium 3 plus, these cations technically can trap this anion and help store it inside the soil. Now, apart from that, imagine that this is the clay particles that we learned earlier. And originally is OH. So it does not have any charge. But by having a H plus attacking this hydroxyl group, it may becomes positive charge. And I think you can guess what conditions is needed. H plus, yes, it's acidic. You decrease the pH, you make them more acidic. Your soil technically will going to gain this H plus from the acidic solution, and the soil itself becomes positive charge. Now, whether or not this is practical or not, I wouldn't say, but this, in terms of chemistry, this is possible. But I would have to say, practically speaking, usually in order to enhance the entrapment of negative charge in the soil, instead of decreasing the pH, usually we're going to add more calcium. Yeah, just calcium, not iron, not aluminium, just calcium. Because why? Calcium, do you know where they come from? Yeah, limestone. Just add limestone, it will also help attracts more negative charge, more anions like nitrate into the soil. So, okay, next one is application of certain cation exchange capacity, soil texture, and so on, liming of soil. Uh, well, I think most of this I already explained to you earlier, so I think I don't want to explain anymore because otherwise it's redundant. Yeah. So it's basically the repetition of what I explained earlier. And we go to the last one, nutrient uptake. So there are three factors that affect soil fertility. Number one, the amount of storage capacity, which is CEC, how much of the storage actually contains nutrient, base saturation, and how easily root take up nutrients. Now, I think earlier I've explained to you about CEC, more CEC, that they're supposed to store more nutrient. However, like I told you earlier, are they bioavailable? Are they accessible and can be absorbed by plants? Not really, actually. Which is why, agronomists, those from agriculture, they also have one more parameters. Not only they want to know CEC, they also need to know percent base saturation. Now, percent base saturation is based on how much of cations that you can leach out from the soil. You see? So you can say that this base saturation, probably the highest value of base saturation is equal to CEC. But most of the time, this base saturation is less than CEC, usually. Why? Because soil, we have micropore, and this nutrient Even though they are like absorbed, they're absorbed, but if they end up in micropore, usually they cannot be like leached out so easily. Okay, now because of that, usually lah, in terms of fertility, to indicate fertility, CEC probably is not the most accurate parameter to indicate fertility. Instead, it's the base saturation. Because base saturation is measuring what are the cations and how much is their concentration that you can leach out, which means these are the available nutrients. Yeah. So base saturation is a better indicator of soil fertility. Yeah. And I think this one is so familiar with what we have discussed earlier. So we just might as well skip to save time. And I think this one I will not going to explain too much. You get what I mean, kan? If I don't explain, you get what I mean lah. But rest assured, now, if you click one of those video that I attached in my earlier slide, one actually explained the entire thing, this entire 3 points. So I think I'll let the video explain to you lah, yeah? Then, okay, so next one. Now, limes, why they are so preferred by farmers, growers. Limes are fertilizer soil with nutrient base. The base replaces the cation. So yeah, why liming is so important? You see, limestone, they are not cheap. Well, technically they're cheap, but not cheap if you want to lime the entire acre of soil. The size actually will factor in, and you might end up having to spend like several, maybe 10K, 10 or 20K just for liming soil. Yeah, I'm not kidding you. You can buy a car by liming once your farmland, which is why when people want to lime soil, they have to think twice. But here is the thing. If you don't lime the soil, your soil may become less fertile. CEC may becomes decreasing over time because of the acidification. Whatnot. Earlier during our discussion about soil acidity, you have learned that over a long period of agriculture, the crops might going to take a lot of the cations away, those such as calcium or magnesium, and eventually your soil becomes less fertile. Because once this is taken, it will be replaced by H+. And guess what? You lose the CEC. Okay? So how do we reverse that? Simple. Put lime. Not only the lime can uh, alter back or neutralize the pH of the soil, they also can bring back the fertility of soil by reversing the decreasing CEC. They re-increase the CEC of the soil, and at the same time, calcium comes back in. So calcium also happens to be a nutrient. Yeah? So the conclusion is that CEC, what do you need to know? Yeah, it's extremely important. Not only CEC tells you how fertile is the soil, that they can indicate, not exactly tell you that, but CEC is more important by measuring the potential of one soil to absorb pollutants and also to absorb nutrients per se. So CEC, there are many strategies we can play around. How do we increase back the CEC so that the soil become more fertile? Frankly speaking, we don't put clay. Once again, clay is not something we add into the soil, but instead we use a simpler method by just adding organic matter. You add organic matter, CEC will come back by itself. Um, well, there's one more thing that you need to do, which is unavoidable, which is by liming. Because only by liming, you can bring back the pH, the alkalinity, and also you can further increase the pH. Plus, you also put some essential elements back into the soil. So for any farmers, these are the two things that they do. They recycle the organic matter, their trees, they fall down, they put it back into the soil, and yeah, they spend a little bit of money, put limestone in. And that will sort everything by itself. So that marks the end of my lecture. Let me unshare this slide, start the presentation, and stop the recording.